Yeah, today I'm going to give a presentation about the work IPGuard protecting intellectual properties of deep neural networks via fingerprinting the classification boundary. This paper is published in Asia CCS 2021, and it is from the group of Jiadong in Duke University. So deep learning models, especially the deep neural networks, have become the standard models for solving many complex real-world problems. However, training a large-scale DNA models is by no means trivial, which requires not only a large scale of dataset, but also significant computational resources. For example, it costs more than 1.6 million to train the BERT models on the wiki dataset over 50 gigabits from the Google companies. So it is thus of importance to protect the DNA from the unauthoritated duplications or reproductions. So one concerning fact is that the well-trained DNA models are often exposed to the public via the APIs, the cloud platforms, or even the open source toolkit. So it gives rise to the adversary, or maybe called the attackers, who attempt to steal the models in a stealth way, causing a serious problems to how to protect the intellectual properties for the DNA models. So the adversary here, we call this model self, attempt to steal a copy of the victim models by different methods. They can mimic the functionalities of the target model, and they used to do some things to make these suspect models cannot be easily recognized by the model providers as a copy. For example, the adversaries may use the model fine tuning method. In this case, so we assume that the adversaries will have the full knowledge about the victim model, since some victim models can be publicly accessed online, including the model architectures or parameters. And then the adversaries will use a small data set to fine-tuning these models. So if this occurs, so the victim open resource models for the academic purpose may be used for some unauthoritated commercial products. And the second way is called the model pruning. The model pruning, in this case, we also assume that the adversary can have the black box access to the victim models from the model providers. And based on the model pruning, the adversaries will first prune the victim models and using some different kind of state-of-the-art pruning method. And then they will still fine-tuning the pruned models with the adversary's small data sets to get a copy from the victim model. By this means, the suspect models can be very dissimilar to the victim model. So it raises a high challenge to identify the pruned model as a copy of the original one. The third method is called the model extractions. In this case, we assume that the adversaries only have a query access to the victim models. So the adversaries may be aware of the architecture of the victim models, but has no knowledge about the training data, the model parameters, or the model structures. And the recently proposed model extractions attacks can help to reproduce the models with the same functionality, with the similar functionalities of the original victim models, without knowing the exact knowledge about the victim models. So by this means, the adversaries can also create a copy versions of the victim models and use them to do some unauthoritated functionalities or some things. So since the model safe have a strong abilities to copy the models, then in this paper, the author consider the threat model here that, here we already, the model owners, that is the providers of the target model, already realized that there were some suspect models that can be a copy of my target model. and it may varies from the different kind of adversaries. And then how can a model owner to verify that this suspect model is actually a copy of my target model? So whether we can verify based on some special fingerprint of the target model, and then if such unique fingerprint is also extracted from the suspect model, the model owners can say that the suspect model is really a copy of my target model. And then they can do some furthering functions to collect the evidence of fulfilling a lawsuit or something. And then, although there were some different kind of methods to verify the fingerprint, such as such some backdoor attacks that used to leave some special patterns on the target model trained by a model owner. However, this kind of method will inevitably influence the training performance of the target models. In this paper, considering that even we want to verify whether my model have been copied by the adversaries, we cannot sacrifice the utilities of my models to some extent. Then whether there are some problems, or whether there is some method to extract such a fingerprint without influence the training phase of the target model. So here in this paper, the author get a key observation that the DNA classifier can be uniquely represented by its classification boundary. Here, the classification boundary is used to divide the data domains into different regions. For example, the regions upper this classification boundary may be classified into the class A, and the area under these boundaries will be classified into a different, maybe the class B. So based on these key observations, the authors proposed this method called the IPGuard to find some data points that are near the target classified classification boundary. Yeah, we can see in this figure that this red point can be some data point just near this boundary. And then the IPGuard will treat this data point and the labels predicted by the target classifier as the unique fingerprint for the target for this classifier. And formally, we will have this function that the X represents the data samples, the Y represents the predicted labels from the target model, and then we can use such a data and label pairs to uniquely fingerprint the target classification model. If a suspect classifier and the target classifier predict the same labels for most of these fingerprinting data points, then the model owners can verify that the suspect classifier is potentially a copy from my target classifier. So different from the backdoor attacks or different watermarking method, this IPGuard method incurs no accuracy loss for the target classifier because it does not temper the training phase or the fine-tuning process of the target model. It's just extracted some special patterns here, the fingerprint, after the model have been well trained. So the training performance of the target model will not be influenced by this fingerprinting method. So I think here the classification boundary idea is the most important part in this paper. And following, I will introduce some technical parts and the experiments on how to implementing such classification boundary fingerprinting. But however, I think the technical part is a little bit facial, and the experiment part will have some problems. I will detail these problems in the following slides. So to implement such classification boundary fingerprinting, the first problems need to solve is how to get the how to determine the classification boundary for the target model, and how to generate the data point just near this classification boundary. So in this paper, the author formulates these problems into an optimization problem. So first, consider that we have a data just on this classification boundary. Then here the Zi and Zj represent the probabilities for this data set, or for this data samples belongs to class I and class J. And we will say that the probabilities will equal if the data is directly on this boundary. And consider there's a distance near this boundary, the distance k. And then the data point in the area of this k distance will have the patterns that the probabilities for this data belongs to class J will larger than the probabilities for this data sample predict to be class K, but the difference between these two probabilities will smaller than the distance K. So motivated by these mathematical relationships, then the authors formulate minimization problems like this. Here the ReLU is a standard ReLU functions that try to get the values, get the max values between 0 and this term. Here the term Zix minus Zgx plus k is to represent that the data samples is near the classification boundary with the distance k. The second term here is to represent that here the data sample is just near the classification boundary between class I and J, because for some practical models, there can be a multi-class classification task rather than a binary class. So if we want to generate some data samples just near the boundary for class I and J, we need to ensure that the probabilities for these data samples belongs to class I and J are the two largest value, so that the second term is trying to make sure this part, while the first term is to make sure that the generated data sample is just in the distance k. So how to solve these minimization problems? In this paper, the author only mentioned that they will use the SGD, the stochastic gradient descending methods to get some feasible value, not directly the optimal values. So, but however, how to transfer these probabilities to the data samples is not mentioned in this paper. So I think this can be I think in this part, we should have, the authors may have some difficulty in how to get the optimal data samples, but however, they avoid this problem in this paper, but just mention SGD method to get some heuristic data samples. And then after get these fingerprinting data samples, the model owners will query the target model and the suspect model to get their predict labels. And the predict labels combined with the data samples will assemble a fingerprint for the target model and the suspect model. And then they will compare this fingerprint to calculate a matching rate. Here the N represents the number of fingerprinting data points. The M represents that how many data points will have the same predict labels. And then they were using this matching rates to measure the similarities between the target model and the suspect model. If this rate is larger than a threshold, the model owners can announce that the suspect model is a copy of my target model. And if this matching rate is lower than a threshold, then the suspect models may not a copy of my target model. So per my understanding, this matching rate is very important in implementing the problems in practical. But however, in the experimental part, the discussion about how to determine such matching rate threshold is missing. As a common side, the authors propose another method to discard this part to avoiding giving a method for determining such matching rate threshold. And the technical part only refer to these two designs. It's very simple. So if there's no questions about this part, I will continue to the experimental part. Okay, I will move to the experimental part. During the experiment, the training three different target models on the CIFAR10, CIFAR100, and ImageNet dataset with three different types of model architectures: the ResNet, WRN, and ResNet 15. And then for the positive suspect model is the model that actually a copy of this target classified. The authors use three different types of method to create this positive suspect model. The first is the phi turning, and they will use the phi turning of the last layer of the target model and all layers to create two different types of suspect model. And here the retrain is just initialize all the weight in the target model, but use a small data set to retrain these parameters with the same model structures. That is called the retrain. Here the retrain is also for the last layer of the target model and all layers for the target model. And for the pruning method, the author introduced two methods called the weight pruning and the filter pruning. That for prune the weight of the target model and the filter. Here the filter mentions activation neurons in the different layers. And these two types of pruning method also implemented with different fractions. Here the P and C represent the fractions of the model that have been pruning. And based on these three methods, the author created different types of suspect model. And here the value here represent the test accuracy for the for the suspect model. We can say that even the adversaries can do some retrain or fine tuning on the target model. This model will still have a good function, will have a good utilities compared to the target model. And then for the negative suspect model, that the model is not a copy of my target model. The author also proposed three methods. First is the same architecture neural networks classified. That we will use the same architectures compared to the target model, but we train these models on ourselves, not from the parameters of the target model, so that these same architecture models, even trained with the same architecture or same data sets, it is not a copy of the target model. Since some data sets are publicly on the website, you can use the CIFAR10. I can also use the CIFAR10. So since I will train this model on ourselves, I will not become a copy of a target model, even on the same CIFAR10 data set. The second method is a different architecture. Here, compared to the same architecture, we will use different architecture. And compared to the ResNet, the author select these different types of architectures. And for the random forest, it is not a pipeline for the neural networks, but also consider this method to train some negative suspect model. And here it is the testing accuracy of this negative suspect model. we can say that this model is still of a good performance to do the target classification task. But however, this model is not a copy, while this positive suspect are actually the copy that we need to identify them. Based on the method proposed in this paper, the author calculate the matching rate between the target model and the positive suspect model. Here IPGuard the IPGuard lines represent the matching rate calculated based on their method. We can say that for this positive suspect classifier, their method can obtain a high similarities between the target model and the suspect classifier, so that it demonstrates that this classification boundary is actually can help to identify the uniqueness of the target model. Here, the FGSM, IGSM, and the CWL2 represent 3 different types of data point generation method. Here, for the IPGuard method, they just choose the data samples near the decision boundary. But for these 3 methods, for these 3 counterpart methods, they just generated some random or adversary samples that try to make the target models output the false predictions, not directly for the fingerprinting. But however, from their result, we can say that the adversary samples can also help in identifying the uniqueness of the target model, because the matching rate calculated based on the samples from this method can have similar values compared to the IPGuard. However, the IPGuard can be a little bit more strong, but these 3 counterpart methods still make sense. When refused to the negative suspect classifier, we can say that the similarities between the target model and this negative suspect classifier is relatively very low, which also demonstrates that their method can actually differentiate the positive suspect and the negative suspect. Since the counterpart method can still get a similar performance, although compare the effectiveness between their method IPGuard to this counterpart method, we can say that the FGSM, IGSM, and random cannot get a good performance compared to the IPGuard, while the calculation time for this method are relatively low, but the performance is lower than the IPGuard. For the CWL2, this method can achieve the similar performance to the IPGuard, but the calculation time is relatively very large. So the effectiveness, so the author announced that the IPGuard can achieve the performance and with a good effectiveness. But however, although based on these tables, we can say that the matching rate between the positive and negative can have a very large difference. But how to define this matching rate in the practical settings is a very important problem. However, the author do not provide the method for determine such a threshold. In contrast, the authors use the discussion for the area under the robustness and the uniqueness area to discuss this threshold. Here, the threshold is represent the matching rate between the target model and the suspect one. Here, the robustness is actually the precision. It's actually the recall that the fraction of the truth of the positive suspect models can be recognized by the method. Here, the uniqueness is the precision that the fractions that the positive and negative models in all predict positive model. Here in this paper, the authors use the robustness and the uniqueness, but actually they just the precision and the recall matrix when we use to evaluate a machine learning method. So considering that for an ideal method, for different threshold, we will always get a we will get a 100% robustness and 100% of the uniqueness, but it is just ideal situations. So for different threshold, we will have a trade-off between the robustness and the uniqueness. So in this paper, the author will calculate the areas under these two curves as the utilities and the trade-offs for the method under different threshold. And the author said that if we can have a large ARUC values, we can say that our method is in good performance. If the area for this ARUC is relatively small, so this method can always is in the bad performance, that the robustness and Unix is all relatively lower. But however, I think this discussion is trying to avoid directly answer the question how to determine such matching rate as the threshold. But I think it is the main limitations of these papers. And actually, I don't know what is your opinions, but in my opinion, if I am a reviewer, I will not accept such a discussion that says that, oh, our method can have a trade-off in all the threshold. Actually, in the practical, I think the best threshold for this machine rate is more important than the overall performance across different thresholds. And in their paper, actually, anyway, they discuss about this area under different value of k. Recall that in this k is the distance between the fingerprinting data point between the decision boundary, and we can say that under different distance, the ARUC values was first increased and then decreased. And in this paper, the author gives the reason that for a small value of k, the generated fingerprint point is directly on the decision boundary, so that the probabilities for this fingerprint point is half and half. So it cannot precisely measure the uniqueness of this decision boundary. When the distance increases to some certain values, this generated fingerprint point can help to better describe the overall this decision boundary. When the distance continue to increase, the generated fingerprint data point is too far away from this decision boundary, so that it still cannot describe the uniqueness of this decision boundary. So the performance continue to decrease. And also, how to define such a value of k is still not proposed in this paper, but just a discussion about this trend. So that is all of the experimental part of this paper. Still, the authors only discuss the distance k and the difference between the similarities between the positive and the negative. So I think that is all of this part of this paper. So after going through all this paper, I think that the idea for this paper, that fingerprinting, the utility of the uniqueness of this target model based on the decision boundary, is actually very interesting and makes sense. But however, the authors leaves many open questions in this paper, that how to determine the threshold, how to determine the distance near the decision boundary. So I think although this paper can have many limitations on their technical and experimental part, but the idea is quite interesting and can motivate us to do a following of papers on this area, that how to generate the unique fingerprint for the target model, and without influencing the training phase of the target model, so that we can help to protect the intellectual property of my trained model, and the testing performance of the models will not be influenced by our protection method.
Jiadong, I have two questions.
Okay.
So one is for the motivation. So in the software like industry today, we have a lot of tools to do the to protect the IP of the software, right?
Right.
How could why we should develop a fingerprinting method like this to protect the model, rather than, for example, I can use existing, for example, software license or software other technique to protect the model like a software, right? Because the AI model is basically a kind of software, right?
Right.
So why cannot we use existing method to protect the model?
Okay, I think, yeah, the authors may consider that we can only get some APIs of these models. So we can only query their model to get the prediction result, rather than get the source code of these two models. So we cannot use the software method to compare their source code to do the do the IP protection. So we can only have the query access. So we need to do the IP protections only on the output vectors, output results of the suspect model.
So how this model is served? So for example, if I'm the user, okay, so I will receive the model, the binary model, or I will only receive some API I can call, but I cannot, receive the binary file of the model.
I think in this paper they consider that we can only get an API, cannot get the binary code.
Okay, I see. So the objective is try to verify whether the API I am calling is the authenticate API rather than the pirate API.
Yes, but I think here is not the user. Is that I am the owner of a target model, and I find that there are some very similar APIs. There's some APIs very similar to my target model.
Oh, I see.
I want to say whether they are
I want to, for example, if I'm the service provider, I want to discover anyone try to copy my service and provide a pirated model like my model, right?
Yes.
Okay. The second question is because we focus on the boundary, right? We're using the fingerprinting data points because the model usually itself will involve some randomness, right?
Right.
So even the same input will sometimes, for a neural network model, we cannot guarantee we have the same output. If you input the same data, like twice, then how can we guarantee if we check the boundary, there's no any like a random results?
I think that in this paper, they will have an assumption that even the boundary may have a small drift based on the randomness, but I think the shape or the overall shape of these classified boundaries will not change a lot. So I think that is why they use the data point near a distance rather than directly on this boundary.
Okay, they somehow have some specific level of tolerance to randomness using the such like a distance.
Yes.
Okay. Okay, I see. Thank you.
Okay, so Jiadong, to that mention, so how many fingerprinting data points that need to be generated?
In the experiment, they generated 1,000 fingerprinting data point, and also mentioned that they do the experiment for the 10,000 fingerprinting data points, but the performance is not increased a lot. So they conclude that we can directly generate it just 1,000 fingerprinting data point. It is enough.
Okay, and 1,000 data points, it will not degrade the model performance, right?
In this method, this generated fingerprint point will not involve the training phase. But after the model has been trained, we will query the trained model to get the prediction labels. So that is why they call their method is will not temper the performance of the target model.
Okay,
they only query the target model with this fingerprinting data, but not training the model with this fingerprinting data.
Okay, I see. Okay, so any other question? Okay, so if no questions, so we are done for today's meeting. Okay, thank you, Jiadong. Thank you, everyone.
Thank you.